This is Pin-Hao Chen, ADL final project for detecting cancer tumor. My uni is phc2121. To begin with this project, uh, we need to basically installing the environment and also some Python library. This project considered two different tumor images as one as a testing set and one as a training set. So basically, we have tumor 091 as our training images and tumor 110 as our testing images. Uh, from this part, we can see that the different dimension for different level for tumor 91, and basically we choose level 3 with dimensions 7,680 and 6,720 as our training target level. Our CNN model are designed by VGG16. I will discuss this later. So basically, we first split our tumor 91, the training images, into little patches by 128 pixels per 128 height and 128 width per patches with level 3, and our batch size is 100. So since all the images have lots of noises point, which like these gray area doesn't have any cells, so we want to focus on where exactly the cells is when we are cutting into patches. Otherwise, we will create lots of noisy patches that is unnecessary. So we can see we will need to focus on the height from 1,000s to about 6,000s to 5,000s, and the width from 2,000s to about 6,000s. And this is the one for our testing, which is tumor 110. When splitting the images into patches, we will create this kind of directory structure. In the training data sets, which storing slide 91 patches, we will have a positive directory with patches with positive label, which means there are tumor, and a negative directory. So just like I mentioned, the images I put inside this generate data set functions, which is cut image into patches. Only focus on the height from 1,000 to 6,000 and width from 2,000 to 6,000 too. Basically, what my cutting method is like, I go through all 128 boxes. So offset is the image shape, which is 128, iteratively, and if there contain at least one tumor, which showing true value in the mask in the mask, then we will take these patches as a positive patch. So this is the the count of our negative images and the count of our positive images, we can see that uh, negative negative image patch are about 13 times larger than the positive image patch. So this is really highly imbalanced data set. So for this project, we need to focus how do we deal with it, and how do we also do data augmentation to in order to make it balanced. Mm, in this project, I provide two different ways to deal with. One, I mean, it's the same ways, but I have used two different methods to work on it. The first is to do data augmentation by image data generator with horizontal flip equals to true. So basically, for one patch, we will generate two different training images. And also, using scikit-learn class weights, compute class weights, to compute the different weights for different labels, which will be a dictionary of a key and a value, and this will be one of the input when we fit data into the model. So basically, we read the data, and then the train class weight for the training set is the negative value. We will put lower weight because they have much more patches, and for the positive, we will put higher rate when we are doing training, when we are calculating the loss functions. And this project we use F1 recall and precisions as our min matrix. Our model using VGG19 without fine tuning. The reason we don't use fine tuning in this project is because we only totally have about 1,200 images, which is not enough for training a good weight for these kind of less uh, data sets. And we use checkpoints to store the weight for each epoch. So if the model when the model is going to overfitting, then we could just go back to some specific checkpoints and to find the best models. So this is the training. We can see that we have loss function precision recall and validation loss, validation precision, and validation recall for our training. And the checkpoint is saved successfully. We can also see that the model that it's not overfitting when epoch 30 we have validation loss to 0.25 and precision to 60.66 and recall about 100% recall rate. So we basically choose checkpoint 30 as our final model. The reason and and we save the model into our Google Drive. The reason why the 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 saved model cannot just load it by the tf.keras load model because the F1 and precision and recall, those functions are not predefined in Keras. So when we want to reconstruct this model, we need to do the similar things right here to load VGG19 and then add flatten it and add a dense 32 layer drop out and the sigmoid for the last layer, and then load load the weight for load the checkpoint 30 weights. So we could so so our model could contain precision and recall functions, which I have explained in this part. So after training, after we have a trained model, we want to uh, using another tumor images to see whether our model do have a good performance. Um, and just like I mentioned before, our testing image is tumor 110. We will do the similar things for when we are cutting the image. We split the tumor 110 to positive and negative patches, and this time we split the whole images because we need to construct the mask back by by the prediction by the prediction factor. So we need to maintain the shape to be exactly the same. The testing class weight is the negative is about 4 times larger than the negative is 4 times larger than the positive labels, which is a little which is more balanced that compared to the training data sets. So we use our CNN best model, which is checkpoint 30, to and put our test data into it in order to predict the classes. We can see the true negative, false positive, and false negative and true positive value right here, and then the precisions, recall, and the F1 score. Precision with about 0.20, and recall is 0.24, and F1 is the average score of recall and precision, which is, so we got about 0.21. According to the score, although we have a good validation score, we doesn't really have a good testing score. The reason is that the tumor is we didn't have enough training set, and but if we're splitting into uh, like smaller patches, we will make the training data become a lot more imbalanced. So uh, and we did and so that's why although we have a really good validation score, the testing score might not be the same, and we also cannot confirm that testing and training are exactly like similar cells images. So that's why using this model, uh, uh, we didn't have a really good testing precision recall F1 score, but although we have a good score for the validation set. The last is so after we got the Y predictions, this is a 0, 1 factor. We need to use this to generate it back the mask, the tumor mask. So we basically just it's a negative way when we are cutting image to patches. We just reconstruct the patches. If the label are the same, are we just put the patches row to row offset, column to column offset to the to exactly the label values. So if the label is 1, which is true, then all the 128 128 mask will be true, and if it is 0, then that will be 0. And then the most important thing one right here is to filter out the noisy. So we can use the tissue pixel value that we generated above to remove the noisy predictions, which is not in the which is the prediction value that is not in the cell. So that could make users more focusing on the prediction on the only in the cell. Mm, and this is my prediction for tumor 110. We can easily compare these with the with the true value, which is right here. So this is the true value for tumor 110, and this is the true value for the tumor 110, and this is our prediction for tumor 110. We can see that there are the red points are densely scattered in around the corner, and there are last red point which is a little bit sparse scattered, which is in the middle. So we can interpret it that, or we can infer it that there might have a tumor in these two areas, since these two areas have lots of red points which and they are densely connected. Although I know it's a little bit hard to observe from this prediction since we didn't have a good model. Uh, but we can slightly infer that like this part have more like more red point connected and they are densely scattered, and you can also see there's like edges around here and right here and right here. So for a medical personnel, they could infer that for these two parts, there might have a cancer tumor, which is quite same as the true value for these two parts. So in conclusion, for this project is that um, it's the data set, the training data set for this images is a highly imbalanced data set, which is quite makes sense for medical data. The positive value always like are less than the negative like negative data sets. And for using VGG19 without fine tuning, literally give us a good validation score, but uh, but we didn't have a really good testing score due to less training data and highly imbalanced data sets. Although we have used the class weight method and data augmentation method when we are training the model. So this is all my presentation for my final project, and I am Pin-Hao Chen. My uni is phc2121. Thank you for listening, and that's it.